Ketogenesis is the metabolic pathway used to make ketone bodies from the metabolism of free fatty acids and ketogenic amino acids. Peripheral tissues use ketone bodies as an alternative fuel source when glucose is not readily available. Ketone bodies are elevated during prolonged fasts, starvation, ketogenic diets, uncontrolled type 1 diabetes in the setting of diabetic ketoacidosis, and chronic alcoholism. Before we talk about these scenarios, let's check out Sketchyland's Candy Distribution Center to discuss what ketone bodies are, how they're made, and how they're metabolized. Welcome to the Wind-Up Key Factory, where all the sweet, sour, chewy, crispy, savory candies and thirst-quenching colas are made. Fun fact, the factory supplies sweets to approximately 5% of the world, including Sketchyland, while contributing to about 10% of new type 2 diabetes cases every year. And on that note, let's get to the good stuff. A wind-up factory, huh? I would not want to be the person who forgets to turn that key. The three main ketone bodies are acetoacetate, beta-hydroxybutyrate, and acetone. They're represented by the sweetened acid candy for acetoacetate, Big Chew bubblegum for beta-hydroxybutyrate, and Sweet 1 for acetone. Wow, that's gotta be like the 5th mitochondria and liver rug I've seen today. Okay, not really, but at least it will remind you that ketone bodies are made in the mitochondria of hepatocytes. Alright, so here's a diagram showing how the ketone bodies are made and broken down. Let's start with ketogenesis. Recall from the triglyceride catabolism sketch, hormone-sensitive lipase first hydrolyzes triglycerides to glycerol and free fatty acids inside adipose tissues. Then, free fatty acids undergo beta oxidation to generate acetyl-CoA, which goes to the liver to make ketone bodies. Besides fatty acids, ketogenic amino acids also produce acetyl-CoA and can be used to make ketone bodies. And that's why they're called ketogenic. In the first step, thiolase combines two acetyl-CoA molecules to form acetoacetyl-CoA. We illustrated a worker pouring 2 acetyl colas into a family-size acetoacetyl cola. Who knows why? Maybe they don't want to waste acetyl cola, or maybe they're using up the leftovers they find in bottles at the park? Gross. I'd still drink it. Next, HMG-CoA synthase makes HMG-CoA from acetoacetyl-CoA and acetyl-CoA. See the worker pouring acetoacetyl cola and acetyl cola into that humongous cola bottle? She's HMG-CoA synthase. The stopwatch will help you remember that HMG-CoA synthase is the rate-determining enzyme during ketogenesis. Just a side note, HMG-CoA is a precursor to cholesterol, but we'll save those details for another time. In the next step, HMG-CoA lyase cleaves HMG-CoA, producing acetyl-CoA and our first ketone body, acetoacetate. The worker cutting the humongous cola bottle and pouring the contents into that candy contraption is HMG-CoA lyase. I bet you didn't know that sweetened acid candy was made with humongous cola. Well, now you know. Sweetened acid candy. So sweet, the kids love it. So sour, it'll burn a hole straight through your esophagus. Anyway, now that we've made acetoacetate, let's move on to the next step, where we make our second ketone body, beta-hydroxybutyrate. Beta-hydroxybutyrate dehydrogenase uses NADH to catalyze this step. Illustrated here is a worker wiping the Big Chew bubblegum machine with a towel while slamming an NADH energy beverage. He's beta-hydroxybutyrate dehydrogenase. Big Chew bubblegum. Bubbles are fun. FDA warning, under no circumstances should this gum be consumed by human beings. Okay, these candies are packed up and ready to go. But where do they go? The liver releases acetoacetate and beta-hydroxybutyrate to the blood, or in the case of these candies, on red conveyor belts. Some acetoacetate undergoes spontaneous non-enzymatic decarboxylation to produce acetone, which is eliminated by the lungs and causes the classic fruity odor. Check out that Sweet 1 candy shooting up a futuristic trachea tube delivery system. Let the little fruits remind you that acetone causes the characteristic, not-so-pleasant fruity odor that everyone is raging about these days. Sweet 1. Need to ruin a date? Eat a Sweet 1 and your breath will do the trick. The remaining acetoacetate and beta-hydroxybutyrate are taken up by peripheral tissues. That's why there's boxes upon boxes of sweetened acid and Big Chew bubblegum inside this peripheral delivery cart, ready to be foisted upon unsuspecting guests of Sketchyland Park. Care to guess where it goes? I'm sure that bumper sticker gave it away. Skeletal and cardiac muscle can rapidly utilize ketone bodies for energy. The brain prefers glucose, but may switch to ketone bodies for energy when there isn't enough glucose available after some time. In contrast, erythrocytes can't metabolize ketones because they don't have mitochondria. As we discussed in the Fates of Pyruvate sketch, erythrocytes can only obtain energy from anaerobic glycolysis. Hepatocytes also can't use ketones for energy because they don't have the enzyme needed to metabolize them. So far, we've talked about how ketone bodies are made and where they end up. Let's now discuss how they're metabolized. But before we do, you should know that ketone bodies are metabolized in the mitochondria of peripheral tissues. First, beta-hydroxybutyrate dehydrogenase turns beta-hydroxybutyrate and NAD+ back to acetoacetate and NADH. Then, beta-ketoacyl-CoA transferase transfers CoA from succinyl-CoA to acetoacetate, making acetoacetyl-CoA and succinate. You'll see a worker with a beta key hanging from his belt sucking on a cola. We could probably assume that he spilled cola over the sweetened acid candy. Yeah, that's kind of like transferring, but more dirty. This person is beta-ketoacyl-CoA transferase. Remember that sucking cola is our recurring symbol for succinyl-CoA. What about the products? Well, acetoacetyl-CoA is the same big cola we talked about before, and succinate, well, is sucky lemonade, aka succinate. As you probably remember from the TCA cycle sketch, succinate enters the TCA cycle. Okay, we finally reached the last step where thiolase will cleave acetoacetyl-CoA to make two acetyl-CoA molecules before going to the TCA cycle. Yeah, it's pretty much the same step we started with, but in the opposite direction. How poetic. Remember the bottle opener strapped on the worker's thigh for thiolase. Say sayonara to these thirst-quenching acetyl colas, for they're headed out to reunite with their Oaxacan hot chocolate friends. If this doesn't make any sense to you, then you better watch our TCA cycle sketch. Alright, so now that you know how ketone bodies are made and metabolized, we can finally talk about the different scenarios where we make lots and lots of ketone bodies. You've probably heard this term called ketosis thrown around, especially if you've been trying to start a diet. Speaking of diets, not eating anything for long periods of time ramps up ketogenesis. While this worker works fast, he should probably eat something before he ends up on the floor, or he won't be working at all. We previously discussed in the gluconeogenesis sketch that non-carbohydrate precursors undergo gluconeogenesis to make glucose during a prolonged fast after glycogen stores have been depleted and there isn't enough circulating glucose in the blood. Oxaloacetate is specifically drawn out of the TCA cycle in order to make glucose. This leads to low oxaloacetate levels, which allows acetyl-CoA to favor ketone body synthesis instead of entering the TCA cycle. People on very low carbohydrate or ketogenic diets make ketone bodies. The body thinks that there isn't any glucose available, so it'll assume it's in a fasting state. The same thing happens here. Oxaloacetate gets depleted, and we oxidize fatty acids to make acetyl-CoA, which enters the ketogenesis pathway. The spilled candy will help you remember very low carbohydrate diets. Ketone bodies are also made during prolonged strenuous exercise, like carrying heavy boxes all over the factory floor. The poor guy is just struggling. Chronic alcohol consumption also leads to increased production of ketone bodies. Why? Because drinking too much alcohol increases NADH and depletes NAD+, resulting in the disruption of the TCA cycle and gluconeogenesis. We drew an alcohol flask in the worker's pocket to help you remember that consuming alcohol stimulates ketogenesis. Alcohol depletes liver glycogen stores in addition to oxaloacetate. So when glucose is unavailable, there will be increased production of acetyl-CoA from fat oxidation, which will drive the synthesis of ketone bodies. Please check out our alcohol metabolism sketch to learn more. Uncontrolled type 1 diabetics also produce ketone bodies even if they have high blood glucose levels after eating. Why? Well, their bodies think that there isn't any glucose available because there's no insulin, and glucose can't enter cells. Therefore, the body thinks it's in starvation mode and ramps up ketone synthesis. Okay, now that you know what physiological states are associated with ketosis, let's talk about what happens when we make too many ketone bodies. Ketoacidosis is a pathologic state that causes a metabolic acidosis and is caused by uncontrolled production of ketone bodies. We illustrated spilled sour candy keys to show ketoacidosis. Uncontrolled type 1 diabetes, chronic alcoholism, starvation in the setting of pregnancy or infection, medications, and toxins are the major causes of ketoacidosis. Before we conclude this sketch, you should know that the urine dipstick test, frequently ordered in many outpatient clinics, can only detect acetoacetate in the urine. Let the spilled sweetened acid candy next to the yellow bucket and mop remind you of this. There are other tests available, but that's for another discussion. Okay, let's wind this up. Get it? Wind up factory? Anyone? Anyone? What's the matter with you? You hate puns or something? Okay, but seriously, let's get out of here. Right after this short review. Peripheral tissues use ketone bodies as an alternative fuel source when glucose is not readily available. The three main ketone bodies are acetoacetate, beta-hydroxybutyrate, and acetone. Ketogenesis takes place inside the mitochondria of hepatocytes. First, free fatty acids and ketogenic amino acids are metabolized to acetyl-CoA. Next, thiolase combines two acetyl-CoA molecules to make acetoacetyl-CoA. Then, HMG-CoA synthase makes HMG-CoA from acetoacetyl-CoA and another acetyl-CoA molecule. Afterward, HMG-CoA lyase cleaves HMG-CoA to acetoacetate and acetyl-CoA. Then, beta-hydroxybutyrate dehydrogenase uses NADH to turn acetoacetate to beta-hydroxybutyrate. Beta-hydroxybutyrate and acetoacetate are released into the blood and delivered to peripheral tissues. Some acetoacetate is converted to acetone in the blood, which gets expired by the lungs and causes the fruity odor. Ketolysis takes place in the mitochondria of skeletal and cardiac muscle and the brain. First, beta-hydroxybutyrate dehydrogenase turns beta-hydroxybutyrate and NAD+ back to acetoacetate and NADH. Then, beta-ketoacyl-CoA transferase transfers a CoA group from succinyl-CoA to acetoacetate, making acetoacetyl-CoA and succinate. Finally, thiolase cleaves acetoacetyl-CoA to make two acetyl-CoA molecules, which enter the TCA cycle. Prolonged fasts, starvation, ketogenic diets, prolonged strenuous exercise, chronic alcoholism, and uncontrolled type 1 diabetes are the main causes for making too much ketone bodies. And some of these conditions may result in ketoacidosis.